Real exam questions. Question 54. Slab design with the aid of yield lines. Determine the bending moment in formula form in X and Y direction of a square slab with side A simply supported on all four sides and loaded with a uniform distributed load Q in ULS persistence. The slab has a total load of 24 kilonewton per square meter. Reinforcement in X and Y direction are the same. The lever arm in the X direction is 130 millimeters and in the Y direction 120 millimeters. And D is the mean effective depth. Determine the reinforcement in the X direction and the reinforcement in the Y direction. Repeat this with an average effective depth and determine the bending moment and the reinforcement. Bending moment in formula form, this is our slab. We will use yield lines, so the axis of rotations are at the supports. We have 4 axes of rotation. When two axes of rotation crosses, the yield line starts and ends at the end of the slab. So these are the yield lines. We say that the yield line of the yield factor in X direction is mx, and this is my. A was 5 meters, the load was 24 kilonewton per square meter. Reinforcement X and Y direction are the same, but not the lever arm. So we know that the plastic bending moment in the Y direction is different from that in the X direction, and the proportionality factor is mu. Mx is equal by definition to 0.9 times the lever arm times the design strength of the reinforcement multiplied by the cross section of the reinforcement. Same is there for the bending moment in the Y direction. Out of those two, we see that the proportionality of the bending moment in Y and X direction is the same as that for the effective depths. But we know from this, because this is the equation, we know that mu is equal to dy over dx. So now we have established this, and we will calculate now the work done by the external forces, which is, of course, the total load multiplied by the mean deflection, which is delta over 3. So the total load is q d8 squared divided by 3. Or you can take 4 times the triangle, like stated here, and then you have a times a over 2 divided by 2 and times delta over 3. So it's the same, but this is much quicker. The work done by the internal forces, it's the bending moment here projected on this axis. That gives you mx times a, and the angle of rotation is, of course, delta divided by a over 2. And we have that 2 times. One time this direction, one in that direction. And for my, we have also exactly the same, but in the other direction. So this is then when we substitute for my equals mu mx, we have this expression. E is equal to d. From that, we can calculate mx, which is then qd8 squared over 12 times 1 over 1 plus mu. And we can also write it when mu is equal to dy over dx. We can easily write mx like this. And then my is, of course, this. Now, we are going to look at the reinforcement. Mx, we have seen, we have determined the formula on the previous slide. We can fill in all the parameters and we find mx is 26 kilonewton meter per meter. The reinforcement in the x direction is the bending moment mx divided by the lever arm and the yield strength of the steel. We added 10% to that, and we find 562 square millimeter per meter. The bending moment in the y direction, we use the formula of the previous slide, and we find 24 kilonewton meter per meter. So the reinforcement in the y direction, we calculate this reinforcement and we find 562 square millimeters per meter. And this is exactly the same. So it's logic that it should be the same because we started with it. Now we will look at the use of mean effective depth. The mean effective depth is 125 millimeters. The work done by the external forces is, of course, total force divided by 3. Of the internal forces, it's now much easier because you only have one m, not mx and ma. So it's 4 times m plus 4 times m is 8m. E is equal to d, and m is then equal to q 8 squared over 24. It's 25 kilonewton meter per meter. You see, this is much quicker to calculate than the previous method. The reinforcement needed is the 1.1 times the bending moment divided by the lever arm and the yield strength of the reinforcement. And we have 562 square millimeter per meter. So you see clearly that you do not need to take into account the different effective depths which you calculate with an average depth, when the reinforcement in the two directions is the same, of course. So that is that you can leave out the factor mu, which makes the door calculation much easier.